My name's Trent, as I was introduced, and today I'm going to talk to you about how computer vision is a 3D problem and not a 2D problem. So all of us have to do computer vision, and we need to find things in RoboCup. Vision is one of our most important sensors. We use it to find all sorts of things, soccer balls, goalposts, field lines, other robots, obstacles, all of these things we need to find. So many of us, approach computer vision. We want to find these objects. So first, let's work through an example. I've got a nice picture here of the NUbots lab. We've got some objects we want to find. We want to find balls, goalposts, and things like that. So how do we approach this? Well, we look at this ball and we think, what kind of shape is this? I'm like, well, looks like a circle to me. And if you have 3 points on a circle, you can define a circle. So if you have some way of using a machine learning network to segment this image, or in the old days we used to use the lookup table to segment the image into what the ball is, and then we can grab the edge of the ball. We can grab 3 points, make a circle. Excellent, well done, we did it. We made a circle, we've got the ball. And now goalposts. Goalposts look like straight lines. So as we all know, 2 points on a line, and you can define a whole line. So we just need 2 points on those lines from our detectors and bam, we have goalposts. Same with field lines, they all look like straight lines too. And this center circle, kind of looks like an ellipse. So 2 points on the lines, on these field lines, we can make lines. 5 points to make an ellipse. And we've got field lines. So that's it, right? Vision's done. My talk is over. But just to be sure, how about we check another example? Oh, sorry. Yeah, so 2 points on a line can define a goalpost, 3 points on a ball, 5 points on an ellipse. We can define all these shapes. But let's do another example. So here's another one. So a lot of the kid-sized robots, they're a bit shorter. They'll be a bit closer to the ground, maybe a bit closer to the ball. It's good to test everything. So let's have a look. So let's try and put a circle around this, just like we did last time. And it's not quite fitting as well anymore, is it? We wanted a circle, but we've got these bits hanging off the edge. It's not really very well fitting. But at least, we can fit these straight lines. These straight lines still look pretty good, although this ellipse doesn't really work very well anymore. It's kind of not very elliptical. So, we can still work with this, right? We can just fit an ellipse to the ball. See, we can fit an ellipse to the ball. It works quite well, or we can just slacken the circularity requirements on our detector. Let the points be a little bit further off, a little bit more error. And before you know it, we have ourselves a circle. Goalposts and field lines look straight. The center circle looks a little worse when we try and fit it with an ellipse when we're down low, but it's not too bad. We can probably handle that. But with the NUbots, we made the decision to move to fisheye lenses because they have great field of view and we have nice fisheye. So let's try that as an example. So we want to find that ball, so I put a nice circle around that. And then we want to find goalposts and field lines, so let's put our straight lines. And what's going on here? This straight line is not very straight anymore. It is terrible. So, we have options. We don't have to do anything yet. We can try and fit maybe a curve. Try and fit a curve to this line here. Try and fit a Bezier or something, a polynomial of some sort. We can still try and fit these shapes. We've still got options. We don't have to do anything drastic yet, do we? But when we look at this image though, this is ridiculous. The goalposts to the field lines to the goalposts make one big curve. Everything's all distorted. The ball isn't circular anymore. This is terrible. Everything's ruined. And I guess we should all go home because vision has become way too difficult. So what is the problem here? So the problem that we are all experiencing is that we're taking a 3D problem and we're trying to solve it within a 2D projection. So to have an understanding of what's actually happening, we need to look at the optics. We need to look at what's actually happening to the light coming in and what's happening when it's coming in and hitting our camera sensor. Because that'll give us an idea about how stuff in the real world is appearing on our screen. So to do that, I'm going to talk a bit about lens projections. So lens projection is how your camera takes the 3D world and squashes it onto a 2D surface. So just how many of you may know, you can't take a globe of the Earth, and you can't ever make a perfect 2D map of that Earth by stretching it out. You're always going to lose some property. You can't take the 3D world from your camera and you can't squash it onto a perfect image and preserve everything. So the most important thing to know about a lens projection is the one function, which is there's a function r equals some function of theta. And what that function means is it takes the angle of incoming light and projects it onto your camera sensor. So if we look over here, we can see incoming light has some particular angle to our lens. And then based on the, the properties of the lens, it'll go and project it down at some distance on the actual camera. So if you look at the 3D view here, spinning around to help explain, the light comes in and then it comes down and hits the sensor. And this R is related to the angle. And you can see the light comes straight through. So the other angle as to where it is on the image comes from which direction the light comes in. So there are lots and lots of different projections. I could probably talk for another half hour about all the different projections. But if you're getting a lens and you don't know, or you didn't know what type of lens it was when you bought it, you just bought a lens, the chances are it'll be of one of two kinds of lenses. There'll be either be an equidistant or a rectilinear. There are others like equisolid and orthographic, but if you got one of those lenses, chances are you bought it for that property. So they have two functions. So one is the rectilinear, which is r equals f tan theta, and the other one is equidistant, r equals f theta. So equidistant is great for wide-angle lenses because distances in pixels, so r, maps linearly to angle. So if you go out 10 pixels, you go out some particular angle. If you go out 20 pixels, you've moved double that angle. While rectilinear is, what this ends up being is it's mapping onto a plane. So if you had a plane, then as that angle increased, the distance would increase as the tangent, because as the triangle. So we use rectilinear all the time because humans love planes. Planes are really great. They're super portable. I would say many of you have a nice plane in your pocket. You're probably watching me on a nice plane in front of you. So they're really convenient because, nice big flat surfaces are great to project things on. So when we take our camera images, and we project them onto a plane. That way, later on, when we show those same images on a plane, such as our monitors or a photograph, it'll look correct because the light that was collected onto a plane is now being shone out of a plane. And that's what makes it look really weird when you look at, say, a fisheye lens and you're like, oh, this looks really distorted. And the reason for that is that we've taken an image that wasn't projected onto a plane, it was projected onto the inside of a dome. And then we're squishing it onto a plane and like saying, wow, that looks all stretched and distorted. But if you, for some reason, ever have a phone where instead of having a flat plane for a screen, comes with a dome, maybe you drop it on something a little too hard, then suddenly these images will look correct because they'll be correctly projected and this image will look distorted. So that's that brings me to my next point that annoys me. This is something that I personally find quite annoying, is that when people are discussing projections, there's often a lot of confusion between the terms projection and distortion. So normally anytime there's not an ordinary rectilinear lens, such as the fisheye lens that we saw, people say, oh, this lens is distorted, and we have to undistort it in order to fix it. So different lenses produce different projections, which are different mathematical models that convert to distance. They're not distortion. So then you ask them, what is distortion? So distortion is deviation from your lens model. So if you took a lens projection, which, as I said, is trying to project onto a nice flat plane, and that instead of it being a flat plane, it wasn't quite a perfect lens, and it ended up projecting onto sort of a shallow dish, and maybe like the ends picked up a bit. So then you might be able to take a flat plane, and you might be able to apply some distortion to correct it to be what you want. So the most commonly used one would be a Brown Conradi model, which is just basically a polynomial equation. So basically, it's like a Taylor series. You can model any function with if you have infinite terms. Lens distortion can model almost any distortion if you have enough parameters, but keyword here is almost. So the most important one, which many of you might run into, is fisheyes. So fisheyes are not distortion. And the way that I know this is I can't make a polynomial equation that fixes a fisheye lens that has more than 180 degrees. It's just not possible. Because what you would be trying to do is you'd be trying to fit a polynomial to a circle. And no matter how many terms you throw at that problem, you're never ever going to get a polynomial equation that bends back on itself. So if we have our dome, which is representative of our fisheye, and we add more and more and more polynomial terms, we might be able to get it down vertical, if we get enough of them, but we're never going to be able to get it to bend back on itself, which is why any fisheye lens with more than 180 degrees field of view, or even when it approaches 180 degrees of field of view, it becomes impossible to undistort it, which is why most of the undistortion functions you'll find online, you'll find they say they won't work for lenses which over 150 degrees of field of view, just because as you start approaching the edges of this, the extremes you have to go to with the distortion, or with the distortion matrices you're trying to do, just they don't work. So what should you do instead? If you're modeling a lens, you first identify what kind of lens it is, whether it's an equidistant fisheye or a rectilinear lens, and then you apply distortion after you've identified your model. And then you can use fewer distortion terms to get a proper one. So in my experience, I have yet to find a lens that required more than 2 polynomial terms to achieve sub-pixel accuracy for the model distortion. While if I used, say, a rectilinear model and tried to model a fisheye lens, often you need 3 or maybe even more polynomial terms in order to get that lens to fit. And once they get to 180, then you may as well just give up. So now that I've explained to you roughly about how all that light's working, I can start talking to you about 3D vision. So this is how we solved that problem from before. We stopped trying to solve what is a 3D problem in a 2D projected space. Most of the objects you're looking at in 2D, like that ball that changed shape and the goalposts that get bent, they become really, really simple problems once you look at them in 3D. And all you need to do that is you need to take your pixel coordinates, run them through your lens equation, and then you'll get a 3D unit vector. And once you've got these unit vectors, you can start to really define the geometry that you're actually looking for, rather than defining what the geometry looks like once you've squashed it through some function. So let's go through a couple of the common objects that we'll want to look for in RoboCup. So first, balls. So in 3D, no matter what surface you're projecting it onto, once you project them back into unit vectors, a ball is a cone. That's the primary thing that it is. It has a central axis that goes through it. And then if you take the dot product of any of the edge points around there with that central axis, you'll get a constant. And doesn't matter what projection we use, whether you're using a fisheye lens, a rectilinear lens, or some other crazy lens that you manage to find, you're always going to be able to define your ball using 3 unit vectors, because 3 unit vectors around the edge of a cone, just like it's an analog to how you can define a circle with 3 points, you can define a cone with 3 unit vectors. And interesting, this also explains why an ellipse fits so well in our original example, because we're taking a cone and we're cutting it with a rectilinear plane. And when you cut a cone with a plane, you get a conic section. And a conic section is, a circle, an ellipse. So that's why those fit so well in that scenario. But you don't need 5 points to find it, you only need 3. So let's look at another thing, which straight lines, golden field lines. So anything that's a straight line in the world can be defined using a segment, a plane segment. So if you take 2 unit vectors on a line and you take their cross product, you will get a normal to the plane that they live on. And then any other point or any other vector that is also coplanar with them will have a dot product with that normal of 0. So using this, it doesn't matter which lens projection we're using. It doesn't matter that our fisheye has bent goalposts. Once you take the actual unit vectors, you'll find they are all coplanar, which is a really simple check to do. So rather than trying to fit some crazy curve, you just need to fit a plane. And it makes your math so much easier. And even the center circle. Well, the center circle is a little more complicated, but once we start thinking about it in 3D rather than 2D, we can find a model for it too. So the easiest way to do this, which we use, is to use the combination of these 3D unit vectors with the robot's IMU. So if we project our vectors to the ground, so after rotating them to be in the same coordinate system as the IMU, we can then divide them by the Z component, multiplied by the height. And then if we ignore the Z component of that result, we will have a 2D circle that sits on the ground. And then we can just use 3 points on that, and we've defined a circle. So we don't have to find complicated shapes in our vision. We just need to work out what the 3D geometry is and then match that to what we want. So there's a number of advantages to using 3D. So the models are simpler. So an ellipse model for a ball is far more complicated than just trying to find a cone. And trying to fit a curve to a fisheye lens line would be tricky. And then even once you had that fisheye line, how would you interpret that back into the real world? What does that mean in the real world? It becomes very, very complicated. And your models are more accurate. So you don't have to slacken your detectors to handle the projection. You don't have to, make your circle detector more lenient because objects near the edge of your screen become ellipses. And we can include IMU data in our 3D detections as well. The goalposts, provided they haven't fallen over, are always vertical, which means that when you take that cross product, if your cross product says, hey, this cross product doesn't, is not parallel, or the normal of it is not parallel with the ground, then you can say, okay, well, this isn't a goalpost, or this goalpost has fallen over. So this is a quick view of the NUbots vision from our system. So if you have a look, you'll see, it may not show up so well, but you can see there's a slightly brighter green dot here, here, and here. So for finding the edge of the field, which our green horizon detector has done, it's only had 3 points because we've made a convex hull. But this convex hull, this point of the field must have poked out slightly further than these two edges. So we've made this whole line using 3 points, and this whole line with 3 points. And these goalposts, we've just defined using 2 unit vectors. And then when we project them back to the fisheye lens, we're drawing them, as they would appear if they were in the fisheye lens. So everything looks all, warped, but in 3D, this is actually very, very simple geometry, and it makes for very simple algorithms. But most of you, or many of you, are probably moving away from classical methods of of vision, and you're moving towards machine learning. So a lot of the times we don't use that. So we're using machine learning to solve some of these problems for us. But the question you've got to ask is, do these same problems that I've just described exist in machine learning? And can we handle them? So the answer is yes, these problems do exist. So when you have your machine learning training, obviously balls at different places on the field are going to look different. They're going to look stretched. And we're going to need to train the machine learning to be able to detect that. Because if it learns, hey, this is a soccer ball, or this is a soccer ball, when it gets to the edges of the screen, it's going to be like, that doesn't look like a soccer ball anymore. So we need to do something different. We need to, give our neural networks enough training data that they can handle all of these different scenarios. And if we don't have them, we can use training augmentation. We can skew and stretch and rotate, and many machine learning algorithms will do that. They'll skew, stretch, rotate, and they'll try and learn what these objects look like. So, but if we wanted to, train it reliably across different lenses, we need even more training data. So if we wanted a fisheye lens, and we wanted to work on a rectilinear and a fisheye lens, we need much more training data. Because now goalposts don't just look like straight lines anymore. They might look like bent lines. They might look like straight lines. So we also need larger networks because we're trying to detect more complicated objects. We're no longer just saying, hey, a goalpost is a straight line. We're saying, hey, goalposts are sort of wobbly lines that might be straight and might not be straight. And this also brings with it a downside. The network can't tell the difference. If I had a bent goalpost in the center of my view, how does the AI know that that is a bent goalpost and not a goalpost that's on the edge of a fisheye lens? Because to the neural network, they will look the same. So there's no real way to tell the difference. So to answer this question, I'm going to talk about how the NUbots has approached to solve this problem. So this was part of my thesis. So we use a technique called the visual mesh. So we take the 3D approach all the way from the start, all the way through the neural network, and all of our logic is done with 3D in mind. The only place that we go back to 2D is when we actually need a pixel coordinate. So we do everything in 3D, and then we come back only to say, this is the right color. So this means that we no longer suffer the problems with projection, and we gain some other advantages, because now that we're working in 3D, we don't have to worry about projection, and we can also take advantage of other things like depth independence. So the main way we do this is through a visual stacking method. So we stack objects so they would appear as they appear on the ground line, so they would touch visually. So you can imagine if this is the camera and we had a ball here, imagine if we rolled that ball forward, we would then end up with another ball here, and you carry on, so on and so forth for as far as you want. But the further you get, this ball shadows part of the ground in front of it. So the next ball that would visually touch it is actually getting further and further away. And if anyone's interested, this is the equation that gives you this shape. And the important thing about this is no matter where the ball rolls along the ground, it is going to have the exact same number of points in it. So it's always going to remain the same size. And when Stefan presented this a couple of years ago, there was also a question that I wasn't there for, which is what happens if the ball changes height? And if you rearrange this part of the equation, so this K here represents the number of intersections. If you rearrange this equation, you can actually pull H, modifications to H out into this K. So basically moving up and down just changes the number of intersections with your ball. So what we do with that is we take the network and we make a graph out of it. So basically all of these are set up with the distances like that. So if you take the points around the object like this, and you do a convolution, which is similar to a normal, what you do with a normal convolution, we take each of the points that are neighbors to that point and we stack them all together and we run, activation layer, etc. Then we can get a neural network that's based on this graph. And we can stay in the 3D world and not have to go back to 2D. We don't have to squash anything onto a plane. And so that gives us our output of our network. So, we can see the ball, we can see the field lines. We get a nice looking result. So we run this on our integrated HD Graphics 650, just our little integrated chip. And we're able to run at hundreds of frames per second on both of our fisheye lenses at 1280 by 1024 resolution. Although that resolution is a little bit misleading because, as you can see, we change the number of pixels we sample as we go further into the distance. So we take better use of our resolution rather than having to reduce our resolution so that we can see objects without running out of speed. So in conclusion, always make sure you use the correct lens model for your camera. That's a very important first step. Use 3D as early and as much as possible in your pipelines. The sooner you move out of the 2D world and into the 3D world, the better your result will be. And when you're thinking about what shape an object is, don't think about what shape does this make on the screen. Think about what shape is this in 3D? What shadow is it casting on my screen? And if you can, try and let your machine learning operate in 3D as well. So the visual mesh code, if anyone's interested, there's a link to it here. It's open source, you can have a look. I'm actually hopefully going to be doing a new update to the visual mesh soon. I was hoping to get it done by now, but I didn't quite get it. And there's also the NUbots code, which uses it if you wanted to have a look at that. So thank you very much. And now I believe there's about 5 minutes for questions. So, we'll just quickly see if anyone has any hands raised in the Zoom. Yeah, Jackie has a question.
Yeah, so I thought that was very interesting. Thanks. One question that I have is, what about other effects like the rolling shutter, the barrel distortion and things like that on the lens? So how do they fit into your model? Like a motion blur and rolling shutter, for example.
Yeah, so you're right. Rolling shutter and motion blur can indeed, affect these. But this is one less effect that you have to deal with. Once you start doing your math in 3D, then you will notice that those effects do cause an influence. Like your unit vectors will start getting skewed as the rolling shutter happens, and you will start to get, motion blur is always going to happen if you have, your exposure can't be fast enough, which we can't always get because, lighting is not always good enough. But rolling shutter you can, sometimes account for by working out how your camera's moving over time, and motion blur is going to cause distortion, but at least it's only one source of distortion, not multiple sources of distortion. Because once you start, getting motion blur along with a perspective distortion, then you can start getting some really complicated geometry that you're trying to find.
Yeah, okay, thanks.
No worries. Yeah, Ludovic has a question.
Yep, I was just thinking, you went a little bit quickly over the height problem.
Yes.
If the ball is nearly at the height, or if you're searching for an object and you don't know the height of the robot, of the object you're trying to find. So for example, the ball is flying, you don't know the height of the ball. How can you use it with the algorithm you proposed?
So we have, well, we're currently working on some other implementations of this system where we, instead of projecting onto a plane, we adjust the angles and things like that, which solve this problem quite well. But I mean, those are still research. But yes, in general, as the ball goes up, you're only okay as long as it doesn't exceed the height of your camera. So that is a problem, that the ball can't get too high and without this being a problem. But we do have solutions to it. The other way that we have done in the past is to take this plane here and then make a mirrored plane above the robot, so that you end up having below and above. So as the ball goes above, you're then trying to plot it against the sky rather than against the ground. And then that can also let you still see the ball when it's above you. But in general, this technique is most useful when you know roughly what size the objects are. So if you were to, have a object that is changing size, it would need more. You'd be passing more of the burden of learning over to machine learning rather than to the geometry. So your machine learning would have to be smarter.
Okay, thanks. We are also using something not similar to what you have, but also using IMU and height of the robot, but that's mainly to identify the size of the region of interest, to have ball recognition or stuff like this. And that's also one of the problem, is when the balls start flying, then everything gets messed up. So yeah, it helps to reduce the burden on machine learning, but there's also problems popping when things change. And another question which I had was the fact that you're going to 3D, but have you thought about using two cameras for going to 3D? Because when objects are near, it's still quite helpful.
Yes. So yeah, we actually do have two cameras in our robots, and we run this system on both of them. And we actually use the detections from both in order to give us triangulation. So we consider the like triangulation of objects. We don't do them as, we treat the two cameras as two independent cameras for sensing, and then we take the inferences from those two cameras and use both of them in combination to give us a better result.
Okay, thanks.
Although I believe one of my other NUbots members is currently working or looking at taking both inputs and combining them at the neural network level. So the neural network gets inputs from both cameras simultaneously to get a better sense of where objects are. Yeah, we got another question, so go for it.
I was just wondering about single shot 6D pose algorithms. Do you think we can also use, like, for YOLO, you can use, like, there are some single shot 6D pose algorithms. Do you think they could be a replacement, or could be?
What the work that we've done so far with these types of networks is still has a lot of room it could improve. So if you look, it's basically a standard feed-forward network in sort of a fully convolutional setting. So it could easily be improved with a lot of different techniques for machine learning, such as single-shot detectors and things like that we haven't actually, had a chance to look into yet. So there's a lot of room to improve this technique over what it is currently.
Okay, cool. Thanks.